Okay, hello everyone. Welcome to LICD Lecture number 36A. Today we are going to discuss the frequency response of Opamp in open loop configuration. Okay, so before jumping into frequency response, let's define what is frequency response. So frequency response will tell us how does the gain of an amplifier respond to different frequencies. Okay, operational amplifier, right? It's an amplifier. So it is a plot. The frequency response is also defined as a plot of voltage gain in dB versus frequency. Fine. So with this note, let's start building up the frequency response for an op-amp into open loop configuration, and let's consider 741 for a discussion. So let's get started. Okay, let me adjust the screen over here to half, so then the relevant theory I can take it out and the diagram remains the same over here. I think this is fine. Yeah, I think this is fine. So we consider the equivalent circuit of 741 op-amp, right? We have seen that before. You have a light pink color dotted line rectangle. So that's how we draw the symbol of an op-amp. It is powered by plus VCC and minus V supply. You have output terminal V out, the two input terminals V plus and V minus. That is the inverting and non-inverting, and they are connected to the very high resistance Ri, which is termed as the input impedance of your 741 op-amp. And the difference between the two input terminal is denoted by VID, and the current flowing into the terminals are called as I plus and I minus. Okay, and next we have over here is the voltage dependent voltage source, that is AOL into VID, where VID is the differential input voltage and AOL is the open loop gain. Okay, and at the output side we have RO, which is the output impedance tied to the output terminal of the op-amp. And we have considered at higher frequency, since these components will be connected via a wire, we will have some stray capacitances present. Okay, so C is my stray capacitance. Again, AOL is my open loop gain of the op-amp, which is around 2 into 10 is to 5 for 741 op-amp. And basically, we will be you know reduce the circuit into this part. So at the output side, we have V out. Here we have a capacitor. Here we have RO, and here we have your voltage dependent source. That is AOL times VID. So we'll concentrate on this basically, and let's find out the transfer function of this reduced circuit. Okay. So let us start. Step number one. It's basically like a voltage divider having an impedance of a capacitance. So V out will be given by 1 upon S into C divided by RO upon 1 plus SC. Okay, into the input source, which is your dependent voltage source, AOL into VID. Now we take VID below in in the denominator on the left hand side. So V out upon VID will be given by 1 upon, let me just expand this term and keep, yeah, 1 upon SC upon RO plus 1 upon SC into AOL. Now we denote this entire expression as a new notation, that is a capital A. Now this is the gain with stray capacitance considered. Okay, so that is the new gain A. So step number 3 will be A will be given by AOL. If we simplify the above expression, we'll get in the denominator 1 plus S into C into RO. Next, this is the Laplace domain, right? We'll convert this Laplace domain into frequency domain. So we substitute S equal to j omega. This will be equal to j 2 pi f. So step number 5 will give us A will be equal to AOL divided by 1 plus j 2 pi RO into C into F. Now from here, we substitute the value of FH as 1 upon 2 pi RO into C, where FH is the higher cutoff frequency or the 3 dB frequency. So your equation number 1 will look like A will be given by AOL divided by 1 plus F upon FH. Okay. Again, I repeat, A will be given by AOL divided by 1 plus J times F upon FH, where FH is given by 1 upon 2 pi RO into C. Okay. Now, if we take the magnitude of this equation number 1, we'll get mod of A will be given by AOL divided by square root of 1 plus f upon fh the whole square, which we call it equation number A. And equation number B will be the phase plot. So the phase of A will be given by minus tan inverse of f upon fh, which is our equation number B. And normally what happens is we have two plots representing equation number A and B. So equation number A is termed as a magnitude plot, which is the magnitude of A versus frequency, and equation B is representing the phase plot, which is the phase angle of your A versus frequency. So if we combine these both, that is magnitude plot and the phase plot, we get a Bode plot, which is nothing but my frequency response. Okay. Now let's go to this. So let's focus on the magnitude plot only. So here it is my magnitude plot expression given by formula number A. Okay, so this is my A. A will be mod of A will be given by AOL divided by square root of 1 plus f upon fh the whole square, which we recall it as equation number 1 again. Let me maximize this now. Okay. Okay, and AOL for 741 Opamp is 2 into 10 raised to 5. Let's check this value. So we'll open up the data sheet of 741. This is the data sheet of 741. And over here, let's check the last signal differential voltage amplification, which is 200 volt per millivolt, which is equivalent to 2 into 10 raised to 5, right? So here we got the value 2 into 10 raised to 5. Now, concentrate on this equation number 1 again. For f equal to 0, straight away we can write mod of A will be equal to AOL. That means if we write in terms of dB, that will be mod of A in dB will be 20 log to the base 10 AOL. That means 20 log to the base 10 into 2 into 10 is to 5. If you calculate this number in a calculator, you will get the gain in dB as 106, right? So the gain will be at f equal to 0 will be 106 dB for 741 op-amp. Now let's generalize equation number 1 in terms of dB. So we can write over here 20 log to the base 10 mod of A will be equal to 20 log to the base 10 into AOL minus, because it is a denominator, so we in logarithmic the division will be converted into subtraction. So 20 log to the base 10 AOL minus 20 log to the base 10 square root into square root of 1 plus f upon fh the whole square. So we got finally one master equation, that is mod of A in dB will be given by 20 log to the base 10 AOL minus 20 log to the base 10 square root of 1 plus f upon fh the whole square. Okay. Now slowly we'll find the other values now. So let's consider f equal to fh, right? Next value. And let's say the higher cutoff frequency is upper cutoff frequency is 5 hertz. Okay, and we substitute the values over here. So 20 log to the base 10 AOL is nothing but your 20 log to the base 10 2 into 10 is to 5, which we found out the value before, which was 106 dB, correct? And now we substitute f equal to fh. So whenever f is equal to fh, it will be square root of 1 plus 1, which will be square root of 2, and 20 log to the base 10 square root of 2 is 3 dB. So 106 dB minus 3 dB will give us 106 dB minus 3 dB will give us 103 dB. So at f equal to 5 hertz, that is equal to fh, my gain will be 103 dB. Now, whenever we increase the frequency by tenfold, let's see now at f equal to 10 times fh. So over here, directly the first number we get it as 106 dB. The second term will be minus 20 log to the base 10 square root of 1 plus, it is 10 times fh, right? So it will be 1 plus 10 square. So that will be 1 plus 100. Square root of 1 plus 100, that will be square root of 111. So if you do this in a calculator, that is 20 log to the base 10 square root of 111, you will get 20.45 dB. So we subtract 106 dB and 20.45 dB, we'll get 85.55 dB, and that's the value of the gain at frequency 50 hertz. Now again we go tenfold higher. Now f will be equal to 100 times fh, that will be around 500 hertz. So over here, your gain in dB will be, here it will be in this formula 1 plus f upon fh. That will be 100 times fh. That will be 100 square. That is 10 raised to 4. So you will get minus 20 log to the base 10 square root of 1 plus 10 raised to 4. Okay, so that will be square root of 10001. Okay, that will be close to 40 dB. So the gain in dB will be 106 minus 40, that is 66 dB for frequency of 500 hertz. Similarly, we'll continue this trend and we'll calculate the gain at f equal to 10 raised to 5 times fh at around 1 megahertz, right? Of at around 10 raised to 5 times fh. So that number, if you calculate it over here, you will get 20 log to the base 10 square root of 1 plus 10 raised to 10, because it's f upon fh the whole square. So if you evaluate this on a calculator, you will get 100 dB. So the gain in dB for frequency of 10 raised to 5 will be around 6 dB for 741. Now, we collect all this information together. Let me just adjust the screen properly. Okay, I have to slightly increase the this thing. I will reduce it to, let's say, reasonable size. Yeah, I think this is clear. This is. So whatever analysis we have just now done from this master equation, that is at f equal to 0, we found out the value of the gain. Then next at let me just reduce it further so that it's clearly visible. Yeah. So at f equal to fh, we have evaluated the gain again. At different frequencies, we evaluated the gain in dB, and finally we got this plot. Okay. So here let's check it. It's the x-axis is the frequency values right from 0 to 1 megahertz. Okay, so basically this will be plotted on a semi-log paper, but x-axis will be a logarithmic plot, and your y-axis is the gain in dB ranging from 0 to 106 dB. You remember at f equal to 0, what was the value of the gain? The gain was 106 dB. That's why we got this. And at f equal to fh, that is around 5 hertz, the gain dropped to around 103 dB. So here it is, 103 dB. And correspondingly, we note down these at various frequencies, the gain in dB, and we join all the points and we get this green color. It is plotted in green. So green color is my green color plot is the frequency open loop frequency response plot for 741 Opamp. Okay. So there are a lot of vital informations which we can extract it from this graph. This is a very, very important frequency response of 741. It will give us the limiting speed to which the op-amp can operate, right? And a very important concept of gain into bandwidth product, which will be a constant. Fine. So let's analyze it further. So now your FH is actually 5 hertz, correct? But it is also called as corner frequency, higher cutoff frequency, or break frequency. It has many names. So now let's start analyzing this frequency response, open loop frequency response. Okay. Now the first observation is at f equal to fh, your open loop gain of the op-amp falls by 3 dB down. Okay. So fh is also known as 3 dB frequency, break frequency, or corner frequency. Okay. Now let's go to the second observation. The second observation says when the frequency f is increased by of 1 decade, that is f is going from 110 fh to 100 fh, your gain falls by 20 dB. That is from 86 to 66 dB. Let's go and see this point. Okay. So here was at 50 hertz, it was around 80, around close to 86 dB. And when it increased by 10 times, it has gone to 66 dB. So that proves that point ki if your frequency increases by a decade, your gain falls by 20 dB. Let's check that here over here also. So over here at around 100 hertz, gain is 80 dB. At around 1K, the gain is 60 dB. Okay, so by 1 decade increase in the frequency, the gain has fallen from 80 dB to 60 dB. Okay, so it means that after f equal to fh, the gain starts falling at the rate of 20 dB per decade. Okay, if you see over here, the rate at which the gain falls per decade change in frequency, is called as rule of rate. Okay, so this rate at which the gate start at which the gain of the operational amplifier starts falling down is called as the roll off rate, which is a very very important and conceptual concept. Okay, now let's consider this again. So roll off rate will be minus 20 dB per decade. Why minus? Because the gain is falling down if a frequency is increased by a decade. Okay. Now point number 5 will be at very low frequencies, the open loop gain of the op-amp is very very high. Correct. Around 10 is to around 2 into 10 is to 5. That is around 106 dB. Correct. And the gain is approximately constant from 1 hertz, from actually 0 hertz, that is DC value, to FH, that is around 5 hertz. Okay, that is a 3 dB frequency. What we are saying over here is at very low frequency, the gain of the op amp in open loop configuration is fairly constant up till 5 hertz according to this number. Okay, now let's go to the sixth point. So as the frequency increases from FH, the gain decreases at a roll off rate of 20 dB. This point we have already seen. Now next, as the frequency f is increased further at a particular frequency, now we are going on increasing the frequency from 5 hertz to 10, 100, 1k, 10k, and a point will reach at what particular frequency the open loop gain of the op amp will be 0 dB. Now you can check it out. The 20 log to the base 10 of 1 will be 0 dB. So 0 dB corresponds to the gain of 1. So this is marked over here. So whenever this green color line crosses this 0 dB x-axis, it's called as your FT. The frequency at which this happens is called as, whenever the gain of the op-amp is 0 dB or a gain of 1, it's called as unity gain frequency, or it's also called as unity gain crossover frequency, and it is denoted by f of t. And for 741, the unity gain frequency is given by 1 megahertz. This value is specified in the data sheet of 741. Okay, and now we come to a very important concept, that is, we have heard about this before. That is the point number 10. The product of the gain and the bandwidth of any at any point on the frequency curve is 1 megahertz. Okay, now first of all let us understand what is the bandwidth. So bandwidth is the range of frequencies over which the gain of the amplifier will remain constant. Correct. So over here, what's the bandwidth of my open loop frequency response for 741? Now let's check that. So the bandwidth over here is 5 hertz. So as you can see over here, the gain of the op-amp is fairly constant till 5 hertz. So the bandwidth of the op-amp in the open loop configuration is very very less. That is around 5 hertz. Now let's check this this fact of that gain into bandwidth product is fairly a constant. So for a gain of 2 into 10 is to 5, the bandwidth is around 5 hertz, and which is a constant number, which will be 10 is to 6. Again, when the gain is 10, means 20 log to the base 10 is 20, it's 20 dB. So when the gain is 20 dB, right, gain of 10, and the bandwidth is 100 kilohertz, again the gain bandwidth product is 10 is to 6. So any point on this curve, it's the gain bandwidth product is a constant. Also, whenever the gain is 100, so gain 100 means 20 log to the base 10 of 100, that will be 40 dB. So 100 into see over here, the corresponding frequency is 10 kilohertz. So 100 into 10 kilohertz, again it is 10 is to 6. And again when the gain is 1 over here, the bandwidth is 1 megahertz. Okay, so as you can see clearly, if you want to increase the bandwidth, we have to reduce the gain, or if you are increasing the gain, the bandwidth will reduce. The product will remain fairly constant, that is equal to 10 is to 6 for 741. Okay, now somewhat very very important concepts. We will see this curve in the data sheet also. In the data sheet also, this curve is normally given. So let's check the data sheet of 741. So this is my data sheet of 741. Let's check, it's fairly will be given over here. Yeah, so see over here, you have this open loop large signal differential voltage amplification versus frequency. So this is the point. It's around 106. If we can, clearly check, and gain is the open loop, bandwidth is around 5 hertz, as you can see, and it's fairly falling down at a rate of 20 dB per decade. Okay, the x-axis is my frequency, and my y-axis is my gain in dB. Open loop, the differential voltage gain in dB. Fine. Okay, and as you can see over here, at around 1 megahertz, the gain is around 0 dB, which corresponds to the gain of 1. So this graph over here, which is given in the data sheet, is the same graph which we are studying over here, as you can see over here. So only thing is we have plotted these things carefully. Fine. I hope that this is fine now, and we can move ahead. Okay, so let's move forward. Okay. So the point 12th observation is this. The 741 op-amp is an internally compensated op-amp which contains a capacitor value of 30 picofarad, which reduces the open loop gain at higher frequencies at a roll-off rate of 20 dB per decade, and thus assures a stable operation. Now, what's the meaning of this? See, let's check the data sheet again. So in the block diagram of this op-amp, we'll see a single capacitor present. Let's check this out. Actually, we are checking the, let's check that out, internal structure of the op-amp. Yeah, here it is. This is the functional block diagram. As you can see over here, in this functional block diagram, this represents the entire, this is what is there inside the op-amp. So there are around 22 transistors, 11 resistors, one diode, and one capacitor. Okay, so this one capacitor, what we are talking about. So this one capacitor value is uh, around 30 picofarad inside the 741 IC. That's why it is called as internally compensated. Now, whenever there is a capacitor, it will actually reduce the speed of the op-amp, and this capacitor is the main reason why the gain of the op-amp falls down after your 5 hertz in the case of open loop gain. So that's why your open loop gain is so much limited. So let's see what are internally compensated op-amps and where are they used. So in instrumentation circuits, the op-amp is required to amplify a relatively slow changing signal from the sensors. Now let's say if you have a temperature sensor LM35. So if you measure the reading in LM35, it will come very slowly because it will take some time for a temperature to change and reflect that in terms of voltage using the sensor. So the frequency of such signals taken from the real world sensors, the frequency is very small. So in those situations, we can use internally compensated op-amps, and therefore it does not require a very good high frequency response. So basically, we can build an amplifier with a bandwidth of very low, that is around 5 hertz, in such applications. So in such and similar applications, we can use internally compensated op-amps. Okay. Now let's go to equation number one. Where is equation number one? Yeah. To implement this equation number one, we must know the value of AOL and the break frequency. So your FH is my break frequency and AOL is my open loop gain. Basically, your open loop gain will be given. And so, however, a typical op-amp data sheet, the value of the unity gain frequency is given instead of FH, right? FH is not normally given. So, how you can find the value of FH? So, FH can be found out by unity gain bandwidth into AOL. So, this is the relation which we can typically find. And with this, we have come to the end of today's lecture. But let us quickly see the frequency response curve in LT Spice first before leaving. Okay, so this is the LT Spice window, LT Spice simulation engine, and we are checking the frequency response demo for a open loop op amp, that is OP07. We have powered up the op amp with a plus or minus 15 volt supply, and we have applied the AC of 1 volt peak magnitude. And let's check the frequency response now. So you remember we got the phase plot as well as the magnitude plot. So this is my phase as well as the magnitude plot. The dotted line is my phase plot. Let's not, we not require it over here. So we delete it. If you see carefully this curve over here and the curve to your left hand side, okay, I'll reduce this. Okay, whatever we have studied just now, it's exactly the same. We have checked this curve in the data sheet. Now we have also simulated it in LT-SPICE. Still the nature of the curve is almost the same, as you can see over here. Clearly it's visible. The nature of the gain is same, or maybe the value might be different, because here we have used OP07 instead of 741. So don't bother about the value. In fact, the bandwidth over here we can clearly see it's around few hertz, not even even lesser compared to 741 op amp, because and the gain is even bigger, right? The open loop gain is even bigger. It's touching around what's the value over here? It's around 118 dB 741 for OP07. 741 it was 106 dB, and the gain bandwidth product at around 1 megahertz. So here if I check it, it's around 758 kilohertz. So your FT of this OP07 transistor is around 758 kilohertz instead of 1 megahertz. It's less, slightly lesser. Okay, so that's the demonstration of a frequency response curve in open loop configuration, and the rate at which it falls is also 20 dB. Let's check that. So I'll take one cursor over here, and I take another cursor over here like this. Okay. Okay, now let's check the 1 decade change in frequency. So let's take it at around let's say 100 hertz. Okay, this is 100 hertz. Now let's check at 1 kilohertz. How much is the value? So this is fairly slightly difficult to adjust. Yeah, I think this is proper now. Let me slightly adjust this number to 100. Yeah, as you can see, cursor 2 is at 100 hertz, cursor 1 is at 1 kilohertz. So the change of gain over here is 75, sorry, 78 dB, and here it is 58.58 dB, and the difference is around 19.97 dB. So that is close to around 20 dB. If I exactly match them, I mean, if I make it exactly equal to 1 kilohertz, and this if I make exactly equal to 100 hertz, I can still get a closer result. Okay, let me, yeah. So over here you can see clearly the cursor number 2 is at 100 hertz and cursor number 1 is at 1 kilohertz. So at 1 kilohertz the gain is 58.61 dB, and at cursor 2 at 100 hertz its gain is around 78.61 dB. So clearly you can see the difference between the gain is, so if you increase the gain by a decade, increase the frequency by a decade from 100 hertz to 1 kilohertz, the gain falls from 78.61 to 58.61. So that is around 20 dB fall in the decade. So here it proves the point that the roll-off rate for this frequency response is also, it's also 20 minus 20 dB per decade. So that's point is also covered. So I guess we have covered all the points in this lecture. So I guess, yeah. So in this lecture, we have covered the frequency response of op-amp in the open loop configuration, and we have derived each and every point. So next lecture will see the similar analysis for the frequency response in the closed loop configuration, considering 741 op-amp. So that's it for today's lecture. Thank you for joining.